Hello viewers, this is Mahmood, and in this video we are going to find the critical points of a function of two variables and also determine whether each critical point is a maximum, minimum or a saddle point. So the given function is f of xy equal x times y squared minus 6 times x squared minus 3 times y squared. So since this function is differentiable in the xy plane, you can see clearly it is differentiable. So its possible critical points will only exist at the stationary points. So to find these points, we need to compute the partial derivatives of the function with respect to x and y and then set them equal to 0. So first we are going to find the partial derivative of the function with respect to x. Okay, so that can be written as f of xy with subscript x. So this is the notation for the first derivative of the function with respect to x. So that is going to be y square. So because y will be treated as a constant. Okay, and the derivative of the second term with respect to x is going to be negative 12x, and the derivative of the third term would be 0. In the same way, the partial derivative of the function with respect to y is going to be f of xy with subscript y is going to be equal. So now we have to treat it x as a constant. So here we have 2 times xy, and then the derivative of negative 6x square would be 0, and the derivative of negative 3y square is going to be negative 6y. Okay, so now we are going to set them equal to 0, that is f sub x xy equals 0 and f sub y of xy equals 0. So here we have y square minus 12 x equal 0. So we get y square equal 12x. In the same way, we can say that 2xy minus 6y equals 0. So now we can take 2y as a common factor. So we left only with x minus 3y equal, x minus 3 equal 0. Now we have to use the zero factor property. That is going to be 2y equals 0 or x minus 3 equal 0. So from the first equation we get y equals 0, and from the second equation we get the value of x, and that is 3. So here we have two cases. So now you can see for y is equal 0, the first equation, that is y square equals 12x, would become 0 equal 12x, and we get the value of x, and that is x equal 0. So it means that our first critical point is 0 comma 0. So 0 comma 0 is the critical point. Okay, now for the second case, that is when x is 3. So the first equation again, y square equal 2x, 12x would become y square equal 12 times 3, and here we have y square equal 36, and then this implies that the values of y is going to be plus minus 6. Okay, so the other critical points are 3 comma 6 and 3 comma negative 6 are the other critical points. Okay, so we have total 3 critical points. So hence we can say the critical points of f of xy are 0, 0, 3, 6 and 3 comma negative 6. Got it? So now in the second part of the question, we are going to show that we are going to check that whether uh, these critical points is a maximum or minimum or saddle points. So the second part of the video is use the second partial test to determine whether each critical point is a maximum, minimum or a saddle point. So first we have to look the second partials test. This is the statement of the second partials test. That is, we have a function of two variables x, y that is continuous, second partial derivatives in a neighborhood of x naught comma y naught. This is basically the critical point. Okay, and the gradient of the function at the critical point is going to be equal to 0, because the gradient of f is basically the first partial derivative of the function with respect to x and with respect to y. So now here we have the discriminant, and we have to find the discriminant of the function at a point x naught y naught, and that can be calculated as the double derivative of the function with respect to x at that critical point multiplied by the double derivative of the function with respect to y at the critical point minus the double derivative of the function with respect to x, y at the critical point whole square. That is basically the discriminant at the critical point. So if the discriminant is greater than 0 and the double derivative of the function at the critical point is less than 0, so then that critical point is basically a local maximum point, or we can say that at that point the function attains the local maximum value. In the same way, when the discriminant is greater than 0 but the double derivative of the function with respect to x at the critical point is greater than 0, so the function attains at the critical point, or we can say the functions attains the local maximum value at that critical point. And when the discriminant is less than 0, so we can say that the function at that point x naught y naught is not an extreme value. So the point x naught y naught is a saddle point. And when d is 0, it means the discriminant is 0, so the test is inconclusive. So we have to check all the three cases. So the first case is basically at the critical point 0 comma 0. So first, what is our discriminant? And the discriminant is basically at a point x naught comma y naught is equal double derivative of the function with respect to x at a point x naught y naught multiplied by double derivative of the function with respect to y at a point x naught y naught minus double derivative of the function with respect to xy at a point x naught y naught whole squared. Got it? So we have to find all these double derivatives of the function. So the first derivative of the function with respect to x is basically y squared minus 12x, and when we take the second derivative of the function with respect to x, that is going to be negative 12. By the same way, the derivative of this function, the first partial derivative of the function with respect to x with respect to y is going to be f sub xy at xy is going to be equal, that is going to be 2y. And now the derivative of the function with respect to y is going to be 2xy and minus 6y. Now you have to take the derivative of this function one more time with respect to y. So that is going to be 2x and minus 6. So these are the double derivatives of the given function. So first we have to check at the first critical point, and that was at 0 comma 0. So the first critical point is at 0 comma 0. Here x naught is 0 and y naught is also 0. So the discriminant is that is d at a point 0 comma 0 is going to be equal. The double derivative of the function with respect to x at 0 comma 0 is going to be negative 12. So we have to put negative 12, then multiplied by the double derivative of the function with respect to y at 0 comma 0. So it's going to be negative 6, and then minus the double derivative of the function with respect to xy at 0 comma 0 is going to be 0 because there is a y, so we have to put 0 here, so it would become 0, and that is 0 squared. So we get here negative 12 times negative 6 is going to be positive 72, and 72 is greater than 0. Also you have to check that f double derivative with respect to x at 0 comma 0, that would become negative 12, and that is less than 0. So by the second partial test, when the discriminant is greater than 0 and the double derivative of the function with respect to x at the critical point is less than 0, so the function attains the local maximum value at that critical point. So here we can say that f of xy attains the maximum value at 0 comma 0. Okay, and the maximum value will be automatically 0, because when you put x0 y0 in the original function you will get 0. Okay, and the maximum value is 0. So now we have to check at the second critical point, and the second critical point was 3 comma 6. Okay, so now here x naught is 3 and y naught is 6. Okay, so the discriminant is going to be equal, d is equal d 3 comma 6 is equal, and now when we have to put into the double derivative with respect to x, when we put 3 comma 6, that gives us again 12 because that is constant. And when we have to put this into the double derivative with respect to y, so here x is 3, so it would be 2 times 3 is 6, and 6 minus 6 is 0, and then minus when we have to put this point into the double derivative of the function with respect to xy. So here we have only y, so we have to put 6 here. So 6 times 2 is 12, and then you have to take the square. So 12 square is going to be 144. So now in this case you can see the discriminant is going to be negative 144, and that is less than 0. So by the result, by the second partials test, when the discriminant is less than 0, so that point is basically a saddle point. Okay, so the conclusion is that 3 comma 6 is a saddle point. Is it okay? Now the third case is at the critical point 3 comma negative 6. Now we have to calculate the discriminant, that is d is equal d at 3 comma negative 6, and that is going to be when we have to put this point into the double derivative of the function with respect to x, that gives us negative 12 again because it is constant. And when we have to put this into the double derivative of the function with respect to y, so x is 3, so 3 times 2 is 6, 6 minus 6 is 0, and then minus when we have to put this point into the double derivative of the function with respect to xy, so we have to put just the value of y, so that would be 2 times negative 6, that is going to be negative 12. Then you have to square the negative 12, so that would become 144. So the discriminant is negative 144, and that is again less than 0. Is it okay? So now by the second partials test, we can say that the discriminant is less than 0. So this critical point 3 comma negative 6 is again a saddle point. Got it?